Thank you so much for this warm welcome, and thank you so much for coming along to this talk today. As you can see from the title, we'll be talking about making the impossible possible. Unfortunately, this is not a magic show. I'm not going to be pulling rabbits out of hats or working out what card that you chose out of a deck of cards. Instead, we'll be talking about distributed systems. We'll be talking about how much we depend upon them, how important it is for us to get them right, whether it's even possible for us to get them right. We're going to take a journey through nearly half a century of academic research and engineering on this ongoing battle to try to work out what is distributed computing, how do we do it, how do we get it right, and how do we build these systems that we all love. I'm going to talk about a whole bunch of different papers today. I hope this will inspire you to look at some of these things and read a bit more about them in the future. So if you go to this QR code, there is a GitHub repository with links to literally hundreds of papers that I'm interested in. And within that list, you'll be able to find all the papers I mentioned today. I'll show the QR code again at the end. Closer to the microphone. See, system's not working properly. So distributed systems are absolutely integral to everyday life. They're integral to my life. They're integral to everyone's lives. When I put together this slide, it was like 11 a.m. in the UK, and this was just a small subset of the distributed systems I had already used in this day. So I had taken the Underground in London, so the British version of the subway, and tapped my card that had been charged to my bank. I had used Google Maps to work out where on earth I was going. I work for Microsoft, so I'd used all the various Microsoft-y things, used GitHub, etc. So distributed systems are just fundamental to the way that we all live our lives. We put a lot of trust into these systems. We sometimes trust them with our most sensitive and personal data. So we really want them to be there for us today, and we want them to be there for us going into the future. These are some very generic pictures of technology and the future. But when we think about it, and when we look at the media every day, we're seeing examples of this, from AI and self-driving cars to IoT and smart cities. And this week we had the Apple Vision Pro announcement, right? So there's loads and loads of technologies that are coming along, and we're all here because we love building and using these technologies. So what could possibly go wrong? Famous last words. So this is Postman Pat and his black and white cat. This is a cartoon in the UK. I watched it growing up as a child. I don't know if we still make children watch this, but it's like a very hearty show about the local postman who works for the Royal Mail, which is the British mail service, and his little cat and their adventures that they go on to deliver mail. And this is a very stereotypically British show, and it's in part because the Royal Mail and the British postal system is very much a integral part of British society. It's very much beloved. And in every town and village in the UK, you'll find the local post office, where you go and you send letters, and each one is ran by the local sub-postmaster. And these sub-postmasters are kind of pillars and foundations of the community, often people who are very kind, very lovely, often older people that are just much loved in every village. But unfortunately, between 2000 and 2014, 900, and bearing in mind, England, little place, 900, a lot of people, 900 of these sub-postmasters were convicted of fraud. They took money from our beloved Royal Mail, they stole it, they were found guilty of this, they were made to pay the money back, some of them were sent to prison, they went through divorces, they went bankrupt, some of them died in prison. So they faced very tough penalties for their crimes of taking money from the Royal Mail, except it turns out they never did it. This was a software bug in the software that we were using. This has been called one of the biggest miscarriages of justice in modern British history, which is quite the claim, as you can imagine. And this picture, which, sorry, it's not the most clear, is some people outside the Royal Court of Justice asking for support for the sub-postmasters and trying to get compensation for these people whose lives were ruined by software. Because when the software said this was the number and the human said this was the number, people decided that the human must be lying because the software couldn't possibly be lying. That's a very serious example, but to more trivial and light-hearted things. I am a Facebook user for my shame, and like many people, I got this notification like a few weeks ago being like, there's a lawsuit because Facebook leaked your data, and like click on this button to join it. And I didn't click on the button, but I did Google it to just get a bit more information. Problem is, didn't know which data leak it was, because when I searched Facebook data breach, there was just so many different examples. So this was just one of them. You can see here that, Meta lost a lot of people's data. It sucks for people and users like me, but also sucks for the company. They got fined. Probably should have been fined more money, frankly, but fined large quantities of money, or what looks to me like a large quantity of money. We trusted this system with our personal data, and we were let down. Another example, I don't know if this is as widely known outside of Europe, but in 2018, there was a very fun and entertaining day where the Visa payment network, which is the main payment network that we use in Britain, went down. And I was one of those people in a supermarket with a basket full of shopping, and like many people, I don't carry cash, and I realized that I just have no way to pay for my shopping, and it was absolute chaos, like literally chaos everywhere, because nobody was able to pay for anything. It felt like the world, having had the pandemic, now I know what it really looks like when the world shuts down. But at the time, it felt like the world was shutting down because this Visa network had gone down. And it was such a shock to people, because this is a system that we depend upon in our lives, and it was just not available. Like, it was just not there for one day. And it was just incredible. Like, how can something so important not be available to us when we need them? Surely we know how to build highly available distributed systems by now. So why isn't this a solved problem? Why aren't these smart people and big companies building distributed systems that work for us? And the first reason is that it's just hard. Like, building any software is hard. Building distributed systems is even harder. There are fundamental limits on what we can actually achieve. There's a tension here between things like privacy and fault tolerance. It's all the fun of concurrent systems, plus all the problems that you get with distributed systems. So like, things can fail. Sometimes things only partially fail. Sometimes nodes can't communicate with one another. There's all sorts of weird and wonderful ways in which things can go wrong. And secondly, I would claim that building distributed systems is actually getting harder over time. So, cloud computing, it's been incredibly popular. Everyone loves to put their stuff in the cloud nowadays. Disclosure, I do work for Microsoft, but cloud computing does give us a lot, right? It allows you to put stuff very cheaply into many places. You can build distributed systems of global scale without investing in infrastructure. You don't have to focus on like managing your machines and upgrading things and all that stuff. You can hand that off to someone else if you choose to. But fundamentally, this is essentially just someone else's computer, and you need to trust them when you give them your software and you ask them to run it for you, and you have to trust that they will do it correctly. And if you look, in tech news in any given week, there's often one example of, one of the big cloud providers having some kind of outage that then has knock-on effects to their users. So fundamentally, we want to work out, do we want to trust cloud providers with our software? And if so, how do we trust them, and why do we trust them? So, distributed systems, it's complicated. So why even bother, right? Why do we want to do this in the first place? The main reason is simply because we don't have a choice. Users are geo-distributed. We have come together today, but usually I'm based in Cambridge in England, and so I would be in a different geographical location to everyone else here in this room. And often we're building systems that are essentially plumbing together other systems that were already themselves distributed. So some systems are just distributed by the very nature of them. There's nothing we can do to get around that. In other cases, there might be legal requirements that tell us that we need to store data of certain customers in certain places. So we can't have one big global payment system because maybe we need a system in Europe that's holding European citizens' data, and then a separate system in America that's holding American citizens' data. Another reason is that some simpler systems simply don't fit inside of a single machine, right? They just need too much in the way of resources. They need too much memory. They need too much network capacity. They need more CPUs. You just can't put them into one physical box. Or you might just not want to try to do that. You might say, this is just very expensive. Commodity machines are the cheapest ones, especially when you're looking at getting machines from cloud providers. So you may choose, for cost reasons, to split up your system across a set of machines instead of buying one big super machine, even if that could be enough for you. Thirdly, and the thing that I'm most passionate about is improving resilience. So we have these machines. They do weird and wonderful things. We hope that we can plumb them together in such a way that we can build something that's reliable on top of these unreliable things. And thirdly, we might want to exploit locality. So we might want to push data closer to the users who are themselves geo-distributed. So this is what we see with things like CDNs. So the main body of our talk today, oh yes, my little picture's working. I only recently joined Microsoft, so I recently started using PowerPoint, so I'm very impressed with myself when things like this actually work. So we're going to take a journey together. We're going to cover literally 45 years of research and engineering. We're going to see a battle that went on and continues to go on between mathematicians and theoreticians who try to prove what's impossible in distributed systems and engineers who are working their way around them to build cool things. There are, of course, far, far more results than I could ever cover in this talk. I teach distributed systems. I give like 12 lecture-long courses, and I still have to cut out many things that I would love to talk about. So there's way more here than I can possibly cover. In fact, one of the papers that I considered talking about on its own, the title of the paper is just Hundreds of Impossibility Results in Distributed Computing. So I'm going to just focus on the papers that I love the most and I think are the most valuable to people who are building technology such as yourselves. These papers follow the theme of what I would call having your cake and eating it, because I'm that kind of person. And that is to say systems that are trying to achieve quite a lot of interesting properties at the same time. So these are systems that are trying to be highly available, systems that are trying to be consistent, systems that are trying to have integrity and consistency. And I will say, asterisks, they're not all actually academic papers. One or two of these aren't papers, but they're just super, super cool, so I put them in anyway. So here's a quick overview of what we're going to cover. We'll see the slide again later anyway, but just to set the context that we're going to be starting all the way in 1970 and coming all the way to today, and I'm going to be ending with a little bit of a highlight about some of the academic research that I'm doing today that we hope will be available in a paper at a conference near you soon. So, yes, another working animation. It's 1978. This is the year that computers were first installed in the White House, and according to the Computer History Museum website, it's when laserdiscs were introduced. Those are sufficiently old that I had to Google what a laserdisc was to discover that these were the precursors to CDs. So this is a long time ago and far before I was born, as you can tell, but already people were beginning to think about distributed systems and how we might build them. So there's this paper. It was published by Leslie Lamport in the Communications of the ACM in 1978. And a few years ago, Leslie won the Turing Award. So this is like the Nobel Prize in computer science. And in the text that the committee provided for why they gave him the award, this was the main paper that they highlighted. So if you want a Turing Award, write a paper like this. So this is the seminal paper in distributed computing. People were thinking about distributed computing even before this, but this really marks the beginning of what we think about as distributed systems research today. In this paper, Leslie was considering what does it mean to order events in a distributed system. At the time, the thinking was that if we want to order events, we would just mark these events with the time. We'd just say, what do I think the time is? I think the time is this, and I'm going to mark an event with this time, and then I'll send some messages, and if anybody needs to decide what happens first or what happened before another thing, then we'll just compare the times, right? Because everybody knows what the time is, right? We can all look at a clock and decide what the time is. Unfortunately, machines don't always work like that. Time isn't always synchronized perfectly, and some nodes can run faster than others. In some cases, depending on how your implementation of time works, time may not even be monotonic, which can really mess up your systems. So we need another way of thinking about ordering of events, and that's the problem that Lamport solved in this paper. He introduced this notion of a happens before relationship. So it's basically causality between two different events. So if I was implementing group chat and I said, hey, everyone who's up for dinner at 7, and then someone said, sure, that works for me, there's a causal relationship there between the message that I sent and the sure that works for me. We would want everybody in that chat to see those two messages in that order. It wouldn't make any sense if people just saw a message that said, sure that works for me, with no other context. You can actually imagine if you how you can really mess this up and make people agree to random things, but if you don't have a causal ordering. So in this paper, Lamport provided a solution to this that's called Lamport clocks now. He didn't name it that, but people after the fact call them Lamport clocks. And it was the first instance of a logical clock. And then we see better things like vector clocks come along nowadays. So let's step forward in time. It is 1982, and this is the year of the introduction for the Commodore 64, which became the greatest selling computer of all time. And Leslie was still hard at work thinking about distributed systems and how they can go wrong. He put together this paper with his co-authors that was published at the ACM, Transactions of Programming Languages and Systems. In this paper, Leslie et al. Introduced the notion of Byzantine False. This is where faulty nodes can behave arbitrarily. So nodes in your distributed system can do whatever they like. They can send whatever messages, they can lose state, they can go wild, have a party, anything can happen. And in this paper, he described this using the analogy of a set of armies. They're all called Byzantine armies, and they've got an enemy city in the middle, and they're trying to coordinate and work out, like, when do we attack the enemy? And we all need to agree exactly when to attack to make sure we agree we attack at the same time, and we overwhelm the enemy. If we don't have a way of reaching agreement between these distributed armies, then some will attack, others will retreat, and then we'll be defeated. So the entire paper, I would definitely recommend reading it. It's a very fun read. I'm not sure it's the most helpful of reads. There's a theme, actually, among some of these papers that they're fun to read, but not necessarily particularly useful when it comes to actual systems. But it is a very fun read to read about kind of thinking about this distributed systems problem without computers whatsoever. Interestingly, what this paper did is prove that no distributed agreement protocol that had n nodes would ever be able to tolerate more than a third of nodes being Byzantine. So that means nodes who fail in these weird and wonderful ways. Why a third? That seems kind of random. I won't make everyone, I do a class where I make everyone go through the proof. I will not make you do this today. I'm not that mean. But it basically boils down to the fact that we want to have an agreement protocol that is both safe, so everyone agrees on the same thing, and live, so the protocol terminates at some point because, the world is moving on. We need to reach agreement with things. Protocols should terminate. That's a nice property to have. When you combine these two things, you basically get this formula that pops out at the end that says that the number of nodes must be greater than or equal to 2f, where f is the number of Byzantine faults, plus 1. If you're just talking about nodes that can stop, so crash faults, then this formula is n equals 2f plus 1. So any minority of nodes in your system can fail, and you can still reach agreement. So this basically split the distributed systems literature into two streams. So there's the protocols that can handle these Byzantine faults. Nodes can be weird and wonderful, or protocols that can handle crash faults, so nodes can stop. And now we have these two different types of protocols, and we define all protocols as either being crash fault tolerant protocols or Byzantine fault tolerant protocols. So it's 1985, and it is the year after, because I couldn't find a fun fact about this particular year, it's the year after the launch of the Apple Macintosh. And this very famous paper came out, The Impossibility of Distributed Consensus with One Faulty Process, and it was published in the Journal of the ACM. This paper, which is often referred to as just the FLP result, which is based off the authors' names, proves what's probably the strongest impossibility result in the entirety of distributed computing. And what it says is this. It says that if you have a set of nodes, they cannot reliably decide even a binary value, so deciding between them yes or no, attack or retreat, over an asynchronous network, if even one of them might fail. They don't have to actually fail. If there is just the chance that one of them might fail, we cannot come up with a protocol that will reliably decide a binary value. This is crazy, and this in many ways should have been the end of distributed systems research. Like, what you're trying to do is impossible. But it turns out if you want a bunch of smart people to work on your problem for many decades, write a paper claiming that it's impossible, and they will spend much of their time trying to prove you wrong. So the proof in this paper basically boils down to the fact that even though if a node might fail, we don't know when or if that node has failed. So if we have an asynchronous network, meaning we don't know how long it's going to take for a message to be delivered, we can send a message to a node and say, hey, are you alive? And they don't answer us. You don't know what's going on. You don't know if the message got lost or the message got delayed. You don't know if the node has failed. You don't know if the person isn't answering your text message because they're asleep, etc., etc. So it's 1988, and we're wondering what to do about the field of distributed systems. We've got this big result that tells us that it's going to be basically impossible to do the thing that we want to do. Steve Jobs unveiled the next computer, and this paper, Consensus in the Presence of Partial Synchrony, was published also at the Journal of ACM. So how are we going to get around this big result that tells us that we can't build a distributed system? We can't even agree a binary value, let alone build some amazing, cool distributed system that's going to handle the payments for the entire world. And there's basically two options. The first option is that we give up. We give up on termination and guaranteed agreement. We say, we'll come up with some approximate protocol, we'll add some randomization, and we'll try to prove that statistically it's unlikely that it will never terminate, and just hope that that's fine. This is the basis for a lot of things nowadays, by the way. It makes me a little sad. The second option is to assume network synchrony. So I mentioned before that the problem was that we don't know if a node's failed because we don't know how long it took for a message to arrive. So let's assume we do know. Let's pick a time, and we'll say all messages that we send are received by the other side within 100 milliseconds. We'll just assume that that's true, right? And then that gets around the problem, because if the node doesn't respond within 200 milliseconds, then we can say that they're dead. That's nice in theory, and this is the basis of many academic papers, but that's about the end of it. This isn't very useful in practice. Networks do weird and wonderful things, and we were supposed to be building fault-tolerant systems. That's why we started with this whole thing in the first place, so we don't want to have this big assumption. And it was this paper that really changed the game and basically re-kickstarted the field of distributed systems. This paper, as you can tell from the title, introduced a model called partial synchrony. So this is a model between synchrony, every message is definitely delivered within a time bound, and asynchrony, we have no idea. We just send a message and hope for the best. Partial synchrony says the system will go through periods of time when it's asynchronous and when it's synchronous. And we only need to worry about termination, or like proving that it will terminate during the synchronous periods. And so this paper basically set out a model for how we can do this, and says that we can essentially borrow all the results from the synchronous side and apply them to this much more realistic model. So basically, we only prove that protocols will definitely terminate and make progress as long as the underlying network is delivering messages in a timely manner, which is actually quite reasonable when we think about it. So it's 1999, And the World Wide Web was born thanks to, in my speaker notes, it says Times Berners-Lee. But Tim Berners-Lee is the one to thank for the World Wide Web. And the ACM Computing Surveys published this excellent paper, Implementing Fault-Tolerant Services Using the State Machine Approach. So up until now, we've been talking about very abstract things, deciding a binary value or a single value between a group of nodes. But like, we want to build real distributed systems, right? That do real cool and interesting things. And it was this paper that formalized the notion of state machine replication. This is a way of taking these kind of building blocks and using them to build something real and interesting. State machine replication is a general approach for taking an application and making it highly available without sacrificing consistency. Application logic is replicated across a set of nodes, and then a protocol ensures that each replica receives the same operations in the same order. And assuming that the application logic is deterministic, which, yes, is a big assumption, I know, the nodes will stay in sync. And this is roughly what it looks like in practice. So you take your application, you replicate it, and you have some kind of log of things that go into it. And as long as each copy of the application sees the same input and it's deterministic, they should stay in sync with each other. So as a high-level idea, this is helpful, but we need to actually work out how to do this and how to actually ensure that each of these applications gets the same sequence of operations in the same order. And this is where this very famous paper comes in. So this is Parttime Parliament by Leslie Lamport. Parttime Parliament provides a solution for how we can make sure that all the logs contain the same sequence of operations. So Leslie published this paper where he describes an algorithm for deciding a single value and then deciding a set of values. And the algorithm, it's one that I spent kind of 2 hours teaching in the class, and it was actually the subject of my PhD. But for today, I'll just keep it very, very high level because it's famously kind of subtle, but I do think it's very fun and worthwhile. Just to say that it's kind of a two-phase algorithm, and what's interesting about it is that in each of these phases, you only need the majority of nodes to agree. So if you think back to before, we mentioned there was like this 2f+1. So what that means is basically if you build a distributed system with, say, 3 nodes, you could tolerate one of those nodes failing as long as the other 2 are okay, because you only need a strict majority to agree when you're trying to reach consensus. A fun little bit of history that I wanted to mention. Leslie's quite a character, and he has a webpage where he includes the story behind every paper that he's written from his perspective, and some of them are real gems. So the fun fact about this is he submitted it in 1990, and it took 8 years. 8 years to be published. I'm an academic, and when it takes like 6 months for me to publish a paper, this is painful for me. So how he waited 8 years, I do not know. But the reason that he gave on his website for why he waited 8 years is that when he wrote the paper, in the same way that he used Byzantine armies attacking a city in his earlier works, in this case, he used this idea that there were some Greek islands. There is a Greek island called Paxos, and he leaned into this analogy throughout the paper. Again, very fun read, not particularly useful. And he was told when he submitted it that he'd have to pull out this analogy and just talk about computers sending messages to each other. And he was upset because, in his own words, I was quite annoyed about how humorless everyone working in the field seemed to be, so I did nothing with the paper. And this is one of the most famous papers now that, many people spend many years working on, and he just decided to sit on it because other people didn't appreciate his sense of humor. So it's 1999, and we have got, at this point, this state machine replication thing, and we've got a solution to distributed consensus known as Paxos, and that works in the crash fault tolerant model, so only when nodes crash. But this paper then came along, Practical Byzantine Fault Tolerance, published in OSDI in 1999. And whilst Paxos only considered nodes crashing, remember we talked before about Byzantine faults, so these faults where nodes can do all sorts of weird and wonderful things. Can we have a protocol that could tolerate those kind of faults? And the answer is yes. So this is what this paper, known as PBFT, Practical Byzantine Fault Tolerance, did. So PBFT at a very high level is a similar protocol to Paxos. The way it works is by in the set of nodes, it elects one of them to be the leader, and the leader goes through a multi-phase protocol to basically decide what operation is going to be added to the log in that state machine. So it's a super interesting protocol. I definitely think it is worth having a look at, but the main things to take away is that it's kind of leader-based and it's slow, and despite the name of the paper being a practical Byzantine fault tolerance, it is not now and was definitely not then, in fact, practical whatsoever. It is very expensive because you have to do quite a lot of rounds when you're doing this to get the security guarantees that you want, and you have to have these 2/3 of nodes. So if you want to tolerate one Byzantine fault, you need 4 nodes to do so. So it's quite an expensive protocol in practice, and it was not really used in the wild for many, many years. So year 2000, this was the year of the first camera phone, and of course the Y2K bug. Eric Brewer stood up in one of the main kind of conferences in this space, known as PodC, and presented in his own keynote this exact slide, where he proposed this idea of what he called the CAP theorem. Technically speaking, it was a conjecture because he had not proved it. So this slide is incorrect, but he does not like it when people point that out. There was, in fact, a paper by some other authors about 2 years later that proved this, so then it became a theorem. But at this point, CAP, conjecture. Bearing in mind, he presented this to a theory conference, so this is a place where people care a lot about whether something is called a theorem or a conjecture. But his conjecture was that between the properties of consistency, availability, and partition tolerance, you could only ever have 2 of them in a distributed system. You couldn't, in fact, achieve all 3. And this is an idea that very much became popular in the distributed systems community, and when people build systems, even today, they will often refer to them as being like a CP system or a CA system, and that is basically taking this idea of confidentiality, availability, and partition tolerance and defining which 2 are the ones that we decided that we would pick because we couldn't have all 3. So essentially, which is the one that we sacrificed? So if it's a CA system, you say, oh, we sacrificed partition tolerance. This has been much criticized as an idea, and there are some brilliant papers. My friend Martin Kleppmann wrote a critique of CAP theorem, which is linked in the thing I shared at the beginning, which is an excellent read. And Eric Brewer actually wrote his own revision of it, where he admitted that this was not the most helpful of ideas, but it's very much a big idea in distributed systems, so I did want to include it. So it was 2008, and I again could not find a fun fact for this year. So it was the year after the first iPhone and 2 years after the launch of AWS. I didn't know whether to put this in here or not, to be honest with you. This is not an academic paper. This was a white paper that was put online. I don't really suggest reading it. If you haven't, it's fine. But it did have a big impact on distributed systems and how we think about them and the research that happens in this space. So I felt I had to include it. The Bitcoin paper was this white paper that popped up on the internet under this pseudonym. And it basically says, like, when we're talking about distributed systems and you're talking about state machine replication and Byzantine fault tolerance, you're always assuming that all the participants, even if they might be faulty, you're assuming that they're essentially one operator of this system. It's a centralized system. One person is kind of in charge and running this thing, and there's like 4 nodes or 7 nodes. Instead, they said, no, we want a distributed computer, basically. We want it to be completely decentralized. We want all different parties to be involved, and we want to somehow establish trust between a bunch of parties that don't trust each other, and we don't want 4 nodes, we want 4 million nodes. And so that's kind of the idea that was put into this paper. And the way that they did this, as many people know, is by burning the planet. And this did, really change distributed systems research. A lot of the research that goes on nowadays is basically the direction of it was changed by this little white paper, popped up on the internet, now has, I think, 26,000 citations. I'm pretty jealous, to be honest. So it was 2000, and actually I'm going to skip this paper because I am running out of time. There we go. It's 2013 now. So this is the guy in this photo is Carl Kinsbury. He is if you want just to watch a fun distributed systems talk, don't listen to me, listen to him. He gives the best and most wonderful talks. But the reason I wanted to include him and this thing called Jepson is that as years went by, more and more people were building open source distributed systems, and often even claiming, like, this system has beaten the CAP theorem, or this system has beaten the FLP result. And what Jepson did, and Jepson is an open source tool that you can grab on GitHub for yourselves. What Carl did with Jepson is he basically took real life distributed systems and put them under the microscope. He tested what their claims were and whether they actually fulfilled these claims. He set up these systems and started crashing nodes, partitioning the network, making clocks go backwards, all sorts of weird and wonderful things. And he writes the most wonderful write-ups, which you can find on his blog. And he's tested many tools. This is a list of some of them, and you may recognize some of these examples. I just wanted to give a few examples from the blog because he is brutally honest. It is very fun to read some of the things that he has to say about these systems. And these are big open source systems that people use at scale, at force. And he says things like, we found stale reads, we found total loss of committed transactions from the log. We have infinite loops, we have aborted reads, data corruption, total data loss on any failover. Not just a specific one, any type of failover. We will lose not just some data, but all data. Locks, however, were fundamentally unsafe. They did not and cannot guarantee mutual exclusion. This is the one thing that a lock is meant to do. And back in the day, he also used to litter these with like the most amazing GIFs and memes. It's just wonderful. So this is not a paper. This is instead like an open source tool and a set of blogs. But to me, this is the best example of like taking real life engineered systems and the theory of how we build distributed systems and trying to smash them together in the real world and seeing what breaks. And the answer is a lot. So it's 2014, and this paper came online. This is In the Search of Understandable Consensus. This was published and won Best Paper Award at Usenix ATC. And as I mentioned earlier, Paxos is infamous for being very difficult to understand. When I say that I work on Paxos, even other computer science researchers are like, oh, wow, that's amazing. That's like magic. It's quite funny because Lamport himself thinks that Paxos is very simple. He writes this often and will tell anyone who will listen that it is not just simple, not just easy to understand. He says he's written in some of his papers that it is inevitable. Like if you just thought about consensus, you would come up with it yourself. If you thought about the problem, you would just derive my algorithm from first principles. It is unavoidable, you would trip over it. Despite being someone who literally has a career in working at this, I have never tripped over it. So the community thinks that this is something that is quite tricky. There's many good reasons for this. One of the many reasons is that in order to build a real-life system, you have to get this state machine replication paper, you have to get this Paxos paper, then you're going to need to deal with reconfiguration, you're going to need to deal with compaction because you don't want this log to grow forever. So you've got to get all these papers about different things and try to bring them together, and you'll probably not bring them together correctly. And so what the authors of this work did is they introduced a new simplified consensus algorithm known as Raft and pitched it as this kind of one-stop solution to crash fault tolerant consensus. So they said, if you implement this, then you will have like a replicated state machine which you can use as the basis for your distributed systems. Raft is pretty simple as far as consensus algorithms are concerned, and many, many people have implemented it. Probably the most famous implementation is etcd, which is the distributed key value store that's inside Kubernetes today. So it's 2019, and we have Raft, so we have a good solution for crash fault tolerant distributed consensus. But this paper came along, again at PodC. This is hot stuff, BFT consensus in the lens of blockchain. And with blockchains on the rise, with Bitcoin, Ethereum, and whatever your favorite blockchain or least favorite blockchain is, people were beginning to look for an alternative to burning the planet. And so they looked to consensus and distributed agreement protocols for a way to do this. And so what this paper did is it proposed this algorithm known as hot stuff, which was used back in the day. It was used by Facebook for their like cryptocurrency offering. But I promise it was actually, like, from an algorithmic perspective, this was an interesting thing. What they did is they observed that PBFT, this paper from all these years ago, actually had something really cool in its idea of Byzantine fault-tolerant consensus, but it wasn't well suited to blockchains. In particular, because you had this leader, the leader could just decide what order things happened in. If you want to, say, run a cryptocurrency on this is not a good starting point, because your leader can just be like, you want to buy all these things and this other person wants to sell them? I'll just swap these around and make a large sum of money. So we need an algorithm that was a bit more fair. We also need an algorithm that was more practical because, as I said, despite the name, not actually a very practical algorithm. But machines have got a lot better, and we can now do the cryptographic operations that we need to a lot more efficiently than we could then. So this is where the hot stuff paper came in, and finally Byzantine fault tolerance was in the mainstream. So this brings us to today. I'd probably say this is the year of AI with GPT-4. Maybe it's going to be the year of the Vision Pro or whatever. And where do we stand? Are we done? Can we trust distributed systems? Have we finally declared victory over those pesky theoreticians with their impossibility results? I shouldn't say that. I'm one of those pesky theoreticians, so... We have made significant progress towards achieving high availability in distributed systems without sacrificing consistency, but there is a lot more work that needs to be done. In particular, the things that I'm most mindful of right now are the confidentiality of data. So we talked a lot about availability of data, but those examples, some of those examples we had at the beginning were about the confidentiality of data. And I think this is something we very much overlook. We have solutions for encrypting data when it's on the network, and we have solutions for encrypting data when it's at rest. But encrypting data during execution or end-to-end encryption of data is something that I think we really do need to look at more. Secondly, Byzantine fault tolerance, BFT, gives us some great guarantees, but it's still ridiculously expensive. It still requires a lot of nodes. It requires different parties to run different nodes. It has many phases going back and forth. So this is quite expensive and still is not used in kind of mainstream classical distributed systems. It's only used in this kind of like blockchain-y world over there. And thirdly, there's the advent of cloud computing. So, I want to think about whether we can establish trust in distributed systems that we put in the cloud without necessarily trusting the cloud providers, and whether we can even establish multi-party trust. So if a group of companies can come together and build a system in which they can all trust and be participants in, that's not even on any of their particular infrastructures, but allows them to kind of share data and cooperate and build cool services together. So I'm a sucker for a good acronym as a distributed systems person. So we saw like CAP and FLP. There's also like ACID and BASE and CALM. This one is CIA, confidentiality, integrity, and availability. And these are the three properties that I'm very interested in whether we can achieve simultaneously in today's systems. So I lead a research project which is called the Confidential Consortium Framework. This is an open source project that is trying to solve these distributed systems problems, building on much of the research I've been talking about today. CCF provides a pragmatic foundation for making multi-party applications on untrusted cloud infrastructure more trustworthy. There's a lot in this system that I could talk about, and I could definitely, if you're interested, I will talk to you until you are trying to run away about this. But the main thing I wanted to highlight in terms of like how do we try to do this is this technology known as trusted execution environments, or TEs. So hardware has changed significantly over the 45 years that we've covered. Computers today look so comically different to how they looked then. You know, comparing my Apple Watch and my phone to the Commodore 64, it's actually hilarious to see how much these computer systems have changed. But in many ways, distributed systems haven't really changed. We still have these nodes. We still run software on them. It's still things go wrong on those nodes. Things go wrong in the networks that connect them. The game hasn't really changed very much. That's why we can still learn so much from papers that were written 45 years ago. But there has been some change in the hardware landscape. Trusted execution environments provide secure, isolated execution, which is confidential and integrity protected, and you can even remotely verify that a machine has this special hardware, the TE, and remotely verify what software is running inside the TE. So you can basically go up to a machine and say, I demand a proof from you that you are running my software, the exact version that I expect, and it will give you a proof that you can actually verify to know that the software is running unaltered in this special trusted execution environment. The discussion of TEs began back in 2013 with this little paper from Intel at a small workshop. But nowadays, we find that there are many offerings on the market, both made by Intel and AMD. And you can also get TEs in the cloud. So there's things called confidential virtual machines, which are virtual machines inside one of these TEs. And there's also confidential containers inside one of these TEs that you can get with some of the cloud providers today. And these TEs are one of the key things that enable us to try to provide confidentiality, cheaper integrity, even when you're on the cloud or in multi-party scenarios. So if you remember that state machine replication diagram we saw before, this is the same thing, but this is putting the application logic inside these TEs. So a review. We've covered a lot. I know this is a hell of a lot, but I wanted to give you kind of an overview of everything that's happened in half a century so that if you want to go and read more, you can kind of pick the bits that are most interesting to you. We've seen that fundamental limits exist on what we can do in distributed systems. We've seen that if you want to get crash fault tolerance in your systems, you can use something like Paxos or Raft. Zookeeper, sorry, is the one that I skipped. And if you want Byzantine fault tolerance, you can use practical Byzantine fault tolerance, albeit not the most practical, or something like Hot Stuff. Jepson is a great tool for testing your distributed systems, and I would highly recommend watching Carl's talks or reading some of these analyses because they're just wonderful to see. And the research that I'm doing at the moment into CCF is trying to build on everything that we've seen today to try to bring more confidentiality to our systems and try to provide Byzantine fault tolerance at the cost of crash fault tolerance. So that's everything from me. Thank you so much for listening. That QR code, again, leads to the reading list with more papers than you can possibly ever want to read. Thank you so much.